Hello and welcome back to Matplotlib for Python developers. Today we're going to begin section 2 on the basic plotting functions of Matplotlib. In the course of the 7 videos in this section, we're going to be looking at line and scatter plots as well as the other plot functions provided by Matplotlib, and we're going to dive into the various options that each of these functions provides for you, how to customize them a little bit, and when to choose the appropriate function for your data type. In today's video, we're going to take a look at the simplest and arguably the most useful methods that Matplotlib provides, the simple line and scatter plots. In this video, we're going to find out what differentiates the scatter and plot methods, when you might want to use these two functions, how you can customize the plots provided by these functions, and a few caveats to be aware of. So let's jump over to our Jupyter Notebook now. If you recall from the last video, the first thing we're going to do is actually import both NumPy and Matplotlib's PyPlot module. We're then going to set things up to look nicely for this screen demo. And let's start with that same simple sine curve we saw in the last video. If you recall, we're plotting here 100 data points between 0 and 10, and the sign of those data points. And as you can see, Matplotlib by default will provide you a nice solid blue curve. This curve, the line, can be changed in its style by either passing the line style argument, as we saw in the last video, or by using the quick format strings with the third non-keyword argument. There's 4 default options provided for you: a solid curve, a dashed curve, a dotted curve, and a dash dotted curve. You can access these using either a single dash, a double dash, a colon, or a dash followed by a period. You can also, rather than plotting a solid line, plot with markers. So you can see here, using the k dot non-keyword argument, I've replaced my line with black dots. I can, of course, have markers and dots by combining the options. So you can see here, by combining a period and the double hyphen or double dash, I have a dashed line alongside black points. Now, oftentimes, you have data sets that are too densely packed for you to distinguish individual data points. So here you can see what I've done is replace my 100 data points with 1,000 data points. And so my individual markers are actually smearing into one another. Luckily for us, Plot provides a convenient way of marking every point rather than every single point. Using the mark every keyword argument, you can do exactly that. So by saying mark every equals 10, this will provide Matplotlib the instructions to mark every 10th data point. And as you can see, when I run that cell, it looks like it did before. Every 10th data point, of course, makes us have 100 points rather than 1,000, just as we were plotting before. These markers can be customized as well. You can not only change the color, so say go from black to red, but also the size of these markers using the marker size or MS keyword argument. So you can see here I can change this size. Let's make it very big here with 40. And of course, there's a shortened version called MS that does the same thing. Now, Matplotlib provides for you a wide variety of different markers. You can see here with this large tuple, these are the various marker shortcuts that are provided. And you can do everything from individual pixels to triangles to weird little crosshair things, pentagons, stars, and everything in between. So there's a wide variety of markers available for you to be able to differentiate between different data sets. I would not recommend, though, producing a plot that requires you to use all of these individual markers. That will tend to be a very messy plot indeed. Now, LaTeX not only can use the built-in markers, you can actually set markers using its LaTeX notation. So by passing a literal string to the marker, I can actually say anything I might want to say with LaTeX. So let's set these markers to a capital sigma. Now, as you can see, each data point has been marked with a capital sigma. And you can do individual words. I can write sign where every data point is. I can even write complex things like equations. Let's do sigma equals capital sigma. And there you go. Now, once again, I would avoid using too complicated choices here because you don't want your plots to become too cluttered. Now, the lines as well are able to be customized. So in the default example we showed before, we can actually pass the keyword argument line width here. And just like marker size, this will actually change the width of this line. By default, our line width is 1, and we can both make that bigger or smaller. You can also take a look at the order in which things are plotted. So let's add a second line here and take a look at which plot goes over top of the other. The first plot to be produced is this blue curve. The second to be produced is the green one, shifted over by 1. And notice that the green plot is over top of the blue plot. If you want to override this default, you can pass the z order argument to your plot calls. And that will actually allow you to set which line goes on top. The larger the z order, the closer to the front. In other words, the z-axis that we're looking down. So if you want an earlier call of the plot method to be on top of a later call, you simply need to set the z order higher than the z order given by the later calls. You can also, in cases where you want to overplot things like this, allow for transparency by passing the alpha argument. So let's take a look at two overlapping lines again. Here you go. Again, you can see the green curve overlaps with the blue curve. But if we set alpha to be 0.5, alpha is allowed to go between 0 being completely transparent and 1 being completely opaque, you can see we can actually take a look as the one curve passes underneath the other curve, and the transparency allows us to see that. The last thing to keep in mind when dealing with the plot method is that array order matters. So the order in which things get lined up, in other words, the line that is drawn from marker to marker, even if those markers are not shown, is done in the order that the values occur in the array. There's no way of Matplotlib to know what the sensible way to connect these data points would be other than doing that. So watch what happens now if we shuffle our x values so that they no longer are ordered in the order of their size. In other words, they're randomly shuffled up. Now, if we plot this curve using just markers, then of course it looks perfectly fine, because even though these are out of order in the array, the sign of an individual value is always that specific value. It doesn't change based on where in the array that thing occurs. But look what happens if we try and connect these markers. We get a big mess because the lines are actually being drawn between individual elements in array order. So our nice little sine curve has been reduced into a spiderweb mess here. So if you don't actually have data points that are ordered in a sensible way to produce a curve like this, you should always err on the side of plotting individual markers rather than a line. Now, you can actually go in and deal with markers in a much more sophisticated way using the scatter method. Now, the scatter method, if you run it with no special arguments, looks a lot like the plot method. Instead of plotting a line by default, though, it plots markers. Markers with, you can see, a black edge around them. Now, these markers can, of course, like before, be colored. So I can pass the C argument, it's a keyword argument, and I can give them a specific color, like red. So far, so good. Nothing I couldn't do before with plot. But watch this. If I pass the cos of x values here, in other words, I'm passing not a single value, but an array to color, it will actually color these points based on the value of that array. And like with the image example I showed in the last video, you can apply a color bar here to see what the values correspond to. Now this is really useful because oftentimes we have a third axis to our data. The positions here in this Cartesian plane tell us two dimensions, the x and y values, but oftentimes data sets have more dimensions than simply two. This color allows us to provide a third dimension. Now, just like with the images, I can change the color maps using the CMap argument. And let's go back to my favorite color map here, Inferno. And just like before, it changes the color map, what's used to map between a large value and a small value, and one color versus another color. Now, oftentimes, these edge colors, these black lines that you see around our markers, can be a little ugly. And oftentimes we want to be able to just see the color of the marker itself. And we can do this using the edge color argument. We can either set the edge color to some color other than black, or, as I prefer, set it to be none. That allows us to plot just the color of the marker itself. So if I do that color array again as my C argument, there you can see I have a nice colored lines without those black circles surrounding them. Oftentimes that can clarify your data, and it's especially useful when your marker sizes are small. So watch what happens here if I set my edge colors back to black, but this time give a much smaller marker. So here you can see these edges have actually completely blocked out our colors. And if I were to give no edge color instead, even though our markers are small, we would actually still be able to see the color that they're providing. Now you can see what I did here is I actually set the size of these data points using the S argument. And just like the color argument, S can be passed an array as well. So let's pass an interesting array here. Let's pass the cube of xvals as the size of our data points here. And what this will end up doing is giving us data points with growing, based on the cube of x value, sizes. This is also another way to provide for you an extra dimension to your data. So now you can see we actually have a plot here that's showing 4 dimensions of data: our y, our x, our color, and our marker size. This allows you to show 4 dimensions of data in what really is a 2-dimensional plane. This is a very useful way of conveying a lot of information in a small plot. Now at this point you're probably wondering, why don't always use scatter? Aside from the cases where I want to draw a line, isn't scatter simply better? The one thing to be aware of here is to be careful about the speed. Now typically scatter and plot for small amounts of data can be comparable in terms of the speed of one versus the other. But for large data sets, like you can see here, what I've plotted is 1 million random data points. The plot method can actually be quite a bit faster than scatter. So unless you actually need the ability to change the color or marker sizes on individual points rather than all of the points together, plot will often be the faster choice for you.